Imagine you are dropped in the middle of the Pacific Ocean, dead of night, pitch black, heavy cloud covers, so there are absolutely no stars to guide you.
And you have no map, no compass, and no phone. Your task is to travel exactly 7,000 miles or around 16,000 kilometers on a specific 10-foot stretch of beach in New Zealand.
Personally, I'd be swimming in circles within 10 minutes and calling for a rescue boat for help, bro.
Yeah, same. It's basically impossible as a navigational feat for a human. Yet a bird with a brain the size of a walnut, and that's why people call each other bird brains for a reason, because birds aren't that smart actually. Um, that specific bird with the brain the size of a walnut, called the bar-tailed godwit, does this every single year flawlessly.
And what's wild is that they aren't even using the same hidden biological radar, or they're sniffing the wind. They're actually relying on one of the most counterintuitive and spooky phenomena that we know, and it's related to physics.
And as always, since we love quantum on this Quark Talk podcast, we're talking about quantum entanglement. Today, we're stripping away all the jargon and all the nonsense to tell you directly how nature secretly has hacked quantum mechanics and how birds are navigating the globe with a quantum compass built right into their eyes.
All right, let's look at this from an engineering standpoint first. Okay, if you're building a commercial drone to fly solo from Alaska to New Zealand, what do you really need?
Okay, so you need an onboard computer or like a microchip of sorts, a lot of sensors, constant GPS feed from a multi-billion-dollar satellite network because you need to know where your drone is, and all of that is just to prevent it from drifting off course, like along with like a battery, actually building the drone, and a lot of other stuff.
Yeah, right. But birds have been doing this like long before we've ever put satellites in space. So for decades or probably centuries, the conventional wisdom was, oh, they just navigate looking at the sun during the day, and then at night they follow the constellation.
And that sounds reasonable at first, right?
Yeah.
Until you track those birds flying through dense fog, under overcast skies, in the absolute pitch black. And all of this is over thousands of miles of completely featureless ocean. It's the same in all directions, right? So it's kind of difficult.
Right. That completely rules out any sort of visual landmarks or stargazing, right?
Yeah.
This
If you
left
can't see the
scientists.
stars,
Sorry?
if you can't see the stars, then there's no stargazing.
Yeah, yeah. Did and this left scientists to come up with only one logical conclusion, right? The
Yeah.
birds have to be reading the Earth's magnetic field somewhere.
Yeah, but that hypothesis immediately hit a massive scientific roadblock. The big problem is that the Earth's magnetic field is like really, really weak, like
Yeah, it's
incredibly weak.
it's about like 100 times weaker than your cheap refrigerator magnet that's holding a takeout menu for you.
Damn, okay. Think about that. If you hold a normal compass, like that's more powerful than the Earth. And that metal needle has to be placed on a frictionless pivot just to let that tiny magnetic force of the Earth turn it. So, how on earth would a squishy, warm, noisy, biological brain, walnut sized brain especially, of a bird detect a force that faint, you know?
Well, to solve that mystery, I guess we have to shrink ourselves down. We have to leave the sky and the oceans behind and zoom directly into the cells of the bird's retina.
Okay. So we're basically doing Honey I Shrunk the Kids, but we're shrinking ourselves. And now we're inside the bird's eyeball.
Yep.
So what's the secret weapon here?
Well, it's a highly specialized light sensitive protein called cryptochrome 4, or
Good
cry
name.
4
Good
for
name.
short. And this lives right inside the retina.
Okay, interesting. So the thing is now CRY4, but I like to call it
Cry.
Cryptochrome 4 because it's just so good.
Just
Such a
say
good name.
cry. Just say cry.
Cry 4,
Yeah.
CRY4. Uh, it's essentially like a light activated switch. Imagine a single blue photon. And when I say blue photon, I mean a photon which is in the frequency and wavelength of blue light, because photons can't actually be blue, but like that's how we describe it as. But
Yeah. Yeah.
jargon aside, that photon is entering the bird's eye and it's slamming directly into this cry4 protein.
You literally said you weren't gonna use jargon, but okay, yeah. So
Yeah, I mean,
coming back, this tiny subatomic collision of the photon into this protein, it starts a biochemical reaction. And the energy from that blue photon knocks an electron completely out of its orbit.
yeah. So it also kicks it technically kickstarts a biological chain reaction. It's kind of like a domino effect, like based on that one reaction that Pratham just spoke about. Based on that, then it literally leaps across a microscopic gap. It jumps from one molecule inside the protein to another neighboring molecule, and it keeps going further and further and further.
Yeah, and that single jump changes everything because now you have what physical chemists, which is the term for people who study all of this stuff. Yeah, physical chemists call this kind of a phenomenon a radical pair.
Just like you and me, we're radically changing the world
Yeah,
by providing them
Quark
such
Talk.
insightful content on Quark Talk. Exactly. So just like that, you have two separate molecules. Each is holding an unpaired, highly active electron, and they're separated physically by just a very small distance. It's extremely small. But because of how they were created, they do also share an invisible, instantaneous connection.
Yeah,
And
they are
what is that
quantum
called?
entangled.
Exactly. So, as we've spoken about before, quantum entanglement is famous for being what Albert Einstein has called spooky action at a distance. But let's give you like a recap on what we've spoken about this earlier, just if you haven't heard that episode. So let's just demystify that, right?
Yeah, yeah, okay. So we'll use like a very simple coin analogy, right? Imagine Arnav and I, we're sitting at a table and we both spin a coin. And normally, whether my coin lands on heads or tails has no effect on what Arnav spins, right? They are completely independent.
Yeah, and we're talking about spinning coins, not flipping coins, because we talk about like electrons and like other particles having like a property of spin, so we're
Yeah.
just calling them spinning coins.
Yeah,
But
no, they don't actually spin, but
yeah,
yeah, we call
yeah,
that property.
it's like a property of called spin. So
Yeah.
whatever, we'll explain that. We have explained some of that later before in the previous episode, but we'll cut out that right now. So Pratham just gave an example of when the spinning coins are completely independent. It's kind of like having independent events.
Yeah.
But if our spinning coins, just like the other stuff that we spoke about earlier, like those two
Electron.
molecules were quantum entangled. Let's say those spinning coins are entangled, quantum entangled, then they're mathematically bound as a single system. So if mine lands on heads, then Pratham's is instantly forced to land on tails, no matter how far apart we take them. And that can be like as far as the edges of the observable universe as well. Because like we don't know how they transfer that information on how each of them have got the other state, but that's how it works.
Yeah, and it it might be faster than light as well. So you can literally place both of them like say more than a light second apart, right? And
Yeah,
you change one and the other instantaneously changes uh
yeah.
faster
This is
than
like
light
this is
could have traveled.
yeah.
So
This is a way that scientists are exploring to like have faster than light communication as well.
yeah.
Like to like convey a message literally faster than light.
So yeah, coming back to our bird,
Birds.
our walnut sized brained bird. Yeah. So inside that bird's eye, there are these two unpaired electrons in the radical pair, and they are like our spinning coins exactly. And they are spinning and their spins are perfectly coordinated.
And those two electrons, you can think of them as existing in a very delicate dance, either spinning in opposite directions, which we call a singlet state, or if they're spinning in the same direction, it's a triplet state.
Wow. Interesting naming. But
Yeah.
yeah. So
Yeah.
because this quantum dance is or the state is so incredibly delicate, it is highly sensitive to external magnetic forces. Hint hint the earth.
Exactly. So despite us like flaming the earth on how bad and how weak its magnetic force is and its magnetic field is, even with a force as weak as the earth's magnetic field, as a bird, say, tilts its head or changes its flight path, that weak magnetic field still exists, and it still gently nudges those entangled spins in the those two unpaired electrons in the bird's brain, in the bird's eyes, and that shifts the quantum. Like you use the quantum entanglement and all that, and it shifts the system back and forth between the singlet and the triplet states. So it switches between both of them having the same spin, and between both of them having exactly opposite spins.
It's absolutely mind blowing, especially for a walnut brain, right? The bird's eye is essentially a living quantum laboratory, if you will, constantly measuring subatomic states.
Yeah, but of course, the bird, on the other hand, isn't sitting there doing quantum calculations in midair, right? It's not a quantum computer. It doesn't know what an electron is. So let's talk about the interface on how. Now I'm talking about interface as if it's a computer again, quantum computer and all. But how does the bird actually experience or like use or take advantage of this subatomic data on these like unpaired electrons in its eyes?
Yeah, how does it know which direction to fly in? You say that okay, this thing happens in its eyes or whatever, but how does it finally find out it has to fly in a particular direction? And this is where biology reconnects with the physics. So the spin state of those electrons, whether they are singlet or triplet, they directly control the chemical reaction that takes place.
Right, depending on the
Yeah.
spin state. The cryptochrome, oh, I love the name cryptochrome. It's CRI for whatever.
Right.
Cryptochrome protein either stays active longer or it relaxes back to its original state quickly. So, because again, this is a domino effect, and because it's a chain reaction, this one, like each small change can change the amount of chemical signals sent to the brain.
Mhm. And because this chemical signaling is happening directly inside the retina, uh, the visual center of the eye, the bird doesn't necessarily feel a magnetic tug in its gut, but it usually sees the magnetic field in some way.
And that's kind of mind-boggling thing to think about, right? It's
Yeah.
visual. That was the answer. So, of course, we can't look into a bird's eye directly because that's simply not possible. You have to be a bird to look through a bird's eye.
Well, we
But
can get a bird's eye view, but yeah, you can't look through the eyes of a bird.
nice dad joke. So, neurobiologists, on the other hand, believe that the magnetic field of the Earth alters the bird's sensitivity to light. So,
Yeah.
as they fly,
Yeah.
they can see like a subtle shifting shadow or like a bright patch overlaid directly onto their normal vision. It's kind of like a heads up display. It's kind of like
Mhm.
AR, augmented reality of sorts, you know?
Yeah.
It's
Yeah.
cool like that. Like an in-flight simulator or like a video game.
It's like wearing the Meta Quest 4 or Apple Vision Pro or whatever you want to call
Yeah,
it,
yeah.
right?
Fair.
It literally paints a compass line across your field of view, except nature has built it entirely out of proteins, photons, and quantum spins.
And suddenly, now that you have a roadmap and you have like a path, flying 7,000 miles across a pitch black, featureless ocean isn't a mystery anymore, right? The bird is just flying towards the light and the shadow painted on its eyes by quantum mechanics. Not that difficult.
Yeah, nature is the ultimate engineer. It took a quantum phenomenon we still struggle to control in cold, extremely sterile labs, and it made it run flawlessly inside a warm, squishy bird's walnut eye. Sorry,
Walnut shaped
walnut
brain
brain
and
and its eye.
yeah.
Yeah.
Yeah, and just it's just not that one place where quantum entanglement or quantum mechanics works perfectly, right? It's everywhere,
Yeah.
and it's incredible.